Okay, welcome to Robotics 2. In today's class, we are going to talk about Project 6, and then I will try to give you some more ideas on how to work out the next part of the problem. And then we will look at Project 7 as well. So first and foremost, let me emphasize that the material in chapter 6 is very important. So what we are trying to do here is we are trying to build an autopilot for a UAV system using a building block approach. So here is what we did in last class. We came up with a role autopilot. What is the function of a role autopilot? The function of a role autopilot is, at the end of the day, the actual roll angle, which is here, the actual roll angle should match the desired roll angle. And all this is taken care by the PID gains and the dynamics of this aircraft. So the linearized dynamics and the transfer function. And now what we want to do, we want to extend this a little bit and then look at coarse hold loop. Now, once again, at this point, I want to clarify what do we mean by coarse. So if you look at the path the UAV is taking, if you draw a tangent, the angle between the path and the direction in which the UAV is headed is nothing but the coarse. Now, if you look at the expression for the coarse, I want you to look at this particular part of the transfer function. This says phi c. So this is the commanded phi. It goes without saying that here there is the roll loop in between. So this commanded phi goes to the roll loop that we discussed earlier, and then the output of the roll loop, as you can see, the first output is P, and then it's get integrated and we get actual phi. So this roll output is fed into G divided by VG, and then it is integrated. And when we do that, what we land up with this chi, which is nothing but the actual angle or the coarse hold. Now there is a lot more discussion that goes in between how the variables get translated and what is the physical interpretation of that. I would strongly recommend that you carefully read section 6.3 from the textbook. So this is an important section wherein actually, if you look at the way the building blocks are constructed, we have separated out an integrator to reject the disturbance, and that has an important implication. Now, if you look at the way the coarse hold loop is implemented, you have to see that this somehow, this external disturbance in the coarse, that is dx, that needs to be cancelled out by our PID gains. So what we are going to do is, as we work through this problem, we are going to start with the coarse hold loop, and then we will try to integrate the subsystem that we constructed in last class. So, and then what we will do is subsequently, once the coarse hold loop is discussed, we would most likely get a stable transfer function, and then we will move on to the lateral autopilot side slip hold. And I will discuss that using the example in the textbook. So I hope that everyone was able to run the script and the Matlab Simulink file that we discussed in last class. So in the passing in last class, I kind of showed you how to construct a subsystem from the Simulink block. So did everyone get that? If not, I will explain this once again. And I'm going to go on to Matlab now. So you should be seeing my screen. Now, this is the system that we constructed in last class. Now, the only change what I have made to this system is actually I selected this system, right click, and then constructed a subsystem. Select the system, right click. You have to right click inside. Right click, and then right click, and then create a subsystem. Once you create a subsystem, you will have the system that is shown over here. Now this is the inner loop. That is, so what is the input to the loop? The input is the commanded role. Output is the actual role. Now what I want you to do is, I want you to go back to your Matlab and open project 6 files. In project 6 files, there is something called as Coarse hold loop SLX. And I want you to open that file. So once you open the Coarse hold loop, this is what that loop looks like. And this loop is similar to the loop given in figure 6.11. So this figure is exactly same as figure 6.11. Everyone got that? Now let's look at how this loop is implemented. And so if you don't have any disturbance, coarse can be approximated to heading because there is roll and yaw coupling. So basically this coarse hold loop is exhibiting that type of coupling. So this is the gain, which is the proportional gain. This is the gain of the integrator. This is the saturation block. This is P gravity. P gravity is the value of the gravity, which is 9.81, and VA is the trimmed airspeed. So what you will do is you will substitute the values. P gravity is equal to 9.81 and PVA as 10, and then click OK. So I'm gonna show you that here. So P gravity should be 9.81 and PVA is 10. Okay. And then I'm gonna save this as solution. Now there is a saturation block, and this saturation block requires what is the phi max and phi min. Please note, phi max is the limit on the yaw, and phi min is the limit on yaw in the negative direction. So if you look at the project, I'm going to open the project. Augment, this is the section 6.2. Augment your Matlab script to compute gains for the coarse hold loop. And the coarse with the roll hold as an inner loop. Tune the bandwidth and damping ratio to get an acceptable performance for the step input of coarse angle 45 degrees. So they did not give us the saturation value, but to be on the safer side, I will just say the actuators saturate at 45 degrees. Minus 45 divided by 180 multiplied by pi. Click OK. So you will notice this block is no longer highlighted. However, these two blocks are highlighted. And these blocks, this is the integrator gain. This is the proportion gain. I will just, for the first try, I will add my proportional gain as 0.7, integral gain at 0.01. Integral gain will always be significantly low compared to the proportional gain. Alternatively, what you can do is you can use the toolbox that we talked about in last class to tune this loop. And now what you can do is you can click run and see if the system runs. Then what you'll observe is indeed system works. And this is the response that we got. However, one thing that is obvious, and you can look at the actuator gains. You will notice the actuator does not go to 45 degrees. Actuators are going to plus 30 and minus 30 degrees. So what this tells me is I have an acceptable performance with these gains. Now what I need to do is I need to implement the roll loop inside this loop. So for that, here is what I'm going to do. I'm going to extend this a little bit. I'm going to extend this a little bit. And then I'm going to go back to the subsystem that I constructed. Everyone got this subsystem? Copy this subsystem and paste this subsystem here. And what I will do in this subsystem is, once the subsystem is pasted, I will remove input and output, and I will attach input from here and output from here. So now what has happened is your roll subsystem. If you double click, this is your roll subsystem. And if you look at the coarse heading or the coarse hold loop, it comprises of the outer loop. Now, please understand this you have to implement for Zagi. These coefficients that I have used in this numerator and denominator are sort of arbitrary for Erosonde. You need to implement this loop for Zagi. Any questions here? And then you should run this loop. And then observe what happens. And you will see that with the roll loop as an inner loop and the heading loop as an outer loop, the performance has changed. Nevertheless, it is going to the desired heading. So we set our heading to minus 25 degrees. So as you can see that in the project, this is project 6. In project 6, set your step input to coarse angle of 25 degrees. So we set our course angle as 0.25, I mean 25 degrees, and now we observe that our aircraft is gone to the actual heading. So what we have done is now our aircraft is stable in roll and stable in heading. KD value for the subsystem. KD value for the subsystem is 0.5. So when you click, so before I go any further, I just want to make sure everybody got this answer. Any questions here? Yeah. So here is what you do for the subsystem. So you select all and then right click. Select all and then right click. And you will see here there is create subsystem. So as soon as you click on create subsystem, a subsystem will be created. But it is important to observe that you cannot just create the subsystem if you want subsystem to have some inputs and outputs. So what you need to do is you need to go to the library browser. You need to look at sources. This is the input. Then you have to go to sinks. This is the output. So you need to add input and outputs to your original block so that the subsystem can be interfaced with the main system. Okay, so you should have 6.2 done. Now let's go to the next part, which is now we have to implement the side slip hold. Now, please understand, this is going to be a little interesting in the case of Zagi, because Zagi does not have a rudder. But I will show you how it is done with the side slip hold. And for side slip hold, you should be looking at figure 6.13. So what I want to do is I'm gonna start sharing the screen. So if you look at, so let's go to the next part. We finish the coarse hold loop. Now what we need to do is we need to look at the side slip. So if you look at, let me add one more slide here. So what does this side slip loop look like? If you look at the side slip loop, you have a summing junction, then you have a proportional gain, then you have an integral gain, then you have an integrator, then this integrator gets added at the summing junction, and then there is one more summing junction. This is where the disturbance of side slip gets added. And then here you have A beta 2 divided by S plus A beta 1. And the output of this is beta. And this beta gets fed over here. Now, if you want to refer this, this is the figure 6.13 on page 105. So what is this side slip loop doing? So you have an integrator gain, you have a proportional gain, and what you have is you have this transfer function. So to find this transfer function, what we need to do is we need to go to the Matlab, and in Matlab, you will have to run the script coeff.m. You will have to run this script, and once you run this script, you will get the value of A beta 1 and A beta 2. And then we have to construct using Simulink this side slip loop. Now, do you want me to show you how to construct this, or are you comfortable constructing this by yourself and find the gains Kp and Ki? For Zagi. So once again, yes, at this point, you will ignore the disturbance. So you will ignore the disturbance. And the reason for that is in the actual UAV, you will tune the gains so that the disturbance is ignored. So do you want me to show you how to construct this, or can you do it? Okay. All right. So I am gonna go back to Matlab. Okay. So what we are gonna do is we are gonna go to Simulink. So new, you should be seeing you can alter the course hold file. Yes, that is also possible. So course hold. So if you look at the course hold file, so you have Kp, Ki, you have saturation, but here your transfer function will now change to alpha B2. So you will have to run this script, and then you have to find out what is A beta 1 and A beta 2. So your A beta 2 A beta 2 is minus 1.86, and your A beta 1, S plus A beta 1 is 1.07. So now your transfer function is something similar. If you want, you can add saturation. So 45 divided by 180 multiplied by pi minus 45 divided by 180 multiplied by pi. You can save as side slip hold. I'll change this to beta. Change this to beta. So beta actual. Beta actual. And this is the beta commanded. And to be honest with you, we want our side slip to be 0. And I'm going to add a value for KP, say 0.7. And I'm guessing, I don't know the exact value. The way to do it is running the toolbox 0.05. Click OK, then run. And then you will see your beta actual is 0. Now, one thing that is a little bit unclear at this point, how good is this controller for disturbance rejection? So if you want to study that, we can actually study the disturbance rejection. So I will go to the library browser. Okay, before I go to disturbance rejection, I just want to make sure everybody is with me so far. Yes, both approaches are good. You can use the values in the textbook, or you can actually use or run the toolbox and get the values. But your transfer function is going to be different. Your transfer function will be based on your Zagi parameters. Okay, everyone got this? If you just want to see how well this is working, you can actually give some non-zero side slip, say 10 degrees, and run and see how it is working. Now you would observe that unfortunately, for a non-zero side slip, the system is not working out, which means the gains are not right. So you want to tune the gains. And that tuning would take some time, but I would encourage you to look at the tuning parameters so that you are able to get the appropriate values. Let me see if gain of -10 works. Now, as you can see, once I added the gain of -10, the system is spot on. So what this tells me that no matter what the side slip is, my system is able to go to the commanded side slip. So before I proceed further, any questions here? Now, one thing, let's see how well this system works for the disturbances. So if you want to simulate disturbances, what you would do is you will add a summing junction block, grab the summing junction block, get it over here. Remove this, add summing junction between the transfer function and the input, and then you can add actually some sort of white noise for the disturbances. And let me see, noise power is 0.1, seed is okay. And what I will do now is I will try to run this and see how it works. And you will observe that because of this disturbance, even though my values are close to the actual values, I have some sort of variation. And what does that mean in terms of controller effort? So if you look at the controller effort, which means this white noise is getting propagated in the controller effort. So the way this is implemented, and this is a little bit interesting, that in the first iteration, you don't have noise. At this summing junction, this disturbance gets added. It passes to the transfer function, and now the disturbance is fed back along with the feedback, and now you have this Kp. So let's see what happens if I increase the value of Kp. See if it is able to reject the disturbance. And I observe that it's rejecting a little bit, but not to the extent that I want. So what I'm going to do is I'm going to add a slightly higher integrator and see what it is doing. I see some improvement, but not a whole lot. So at this point, what you want to do is, if you really want to design a controller for disturbance rejection, here is the way to do it. Go to apps, then go on to the control system tuner. And the control system tuner will open. You can, for tuning, select blocks, add blocks, and it will show you the list of the blocks. So I want Ki and Kp. Okay, I'll answer your question just a second, Zubir. Then you have to go to the tuning goals, and then you will see there is disturbance rejection. And in the disturbance rejection, you have to select the disturbance input, and you'll say this is the disturbance. And then you have to see the step response input, output, which is select from the model, which is this guy. And then response characteristics, and click OK. And it's running its own numerical optimization, and then it will show you that this is what it got. Then it will show you what is the value of KP. So run. See if KP gets implemented, and as you can see, this KP value is very, very high. This KP value is very high. Okay, I'm gonna implement this value here. And then I'm gonna implement the KI value. Ooh, KI value is very high too. And let's see if this tuning, what has been done for disturbance rejection. I will save this as Coarse side slip hold loop with disturbance. And run and see if it's able to reject the disturbance. Many a times in actual practice, it may or may not reject the disturbance, or the amount of controller effort that is needed to reject disturbance is beyond the scope of what control system can provide. So as you can see here, this tells me that to reject that disturbance, just using KP and KI, the amount of control effort that is needed is super duper high. So what I'm gonna do is, just for the demonstration purposes, I will remove the saturation block and attach this over here to see if our disturbance rejection scheme is working or not. So what this means is, with purely KP and KI, that disturbance rejection may be possible, but amount of control effort that is needed to reject that disturbance is quite high. And that's why you can see the simulation is running very slowly. Okay, to answer Zubir's question, the way it is done is you start with the system dynamics. So for an example, if you look at the side slip control loop, this figure 6.13, we actually derived this in chapter 5. And I will show you, I'll give you where we derived it. So in chapter 5, page 71, figure 5.4. So figure 5.4, page 71 is where the side slip dynamics was derived. And what we are doing is we are using that linear model to come up with the actual controller equation. So I would encourage you to take a look at the last chapter and kind of correlate with what we are doing. By the way, any questions on disturbance rejection? Can we move on to the next part? So as far as project is concerned, we did 6.1, we did 6.2, we did 6.3. And the last part is pitch, attitude, hold loop. And this pitch attitude hold loop is part of the longitudinal autopilot. So now what I'm going to do is I'm going to go to the longitudinal autopilot. You can keep this script running and you will see gradually you will see some results here. So now I'm going to go to the discussion of longitudinal autopilot. Okay, so the next part is the longitudinal autopilot. And here are a couple of things that you want to be very clear about. So if you look at the longitudinal autopilot, you have pitch angle, airspeed, and altitude. Now these three variables, they correspond to the forward flight of the aircraft. So pitch angle is basically the angle here. This is the pitch angle, which is theta. Airspeed is VA, and the altitude is how far the value of H is. These three things are intimately related with each other. So what it means, I give you an example. Imagine if aircraft pitches up. Okay, just imagine aircraft pitches up. As soon as the aircraft is going to pitch up, the angle of attack, the effective angle of attack is going to increase, will increase. With increase in the angle of attack, lift will increase. With increase in the lift, the altitude of the aircraft will increase. Now, one thing that would happen here is as the aircraft is pitching, the actual airspeed, VA, will decrease. What that means, decrease in the airspeed would decrease the lift. Decrease in the lift will decrease the altitude. And that will result into aircraft pitching forward. The other thing that you need to keep in mind is the thrust. Thrust is actually pushing the aircraft forward. So this is thrust. And depending upon what the flight regime you are in, you are interested in level flight, climbing up, or steady state forward. So the important part is when you're looking at the longitudinal flight, you need to not only look at the relationship between the pitch, altitude, thrust, and the airspeed. You want also to note in what state the aircraft is, whether the aircraft is taking off or aircraft is at constant level flight or aircraft is beyond critical flight regime. So you want to make sure that these transitions are done properly. And these transitions are achieved by means of something called as the state machine or state flow. So what it means is the dynamical system or the transfer functions in state 1 is different compared to the transfer function in state 2. And what dynamical equations to be used, it actually depends upon the commanded input and the current state of the aircraft. So what we want to do is, we want to look at, first and foremost, the relationship between the pitch and the elevator. So for in an aircraft, the control of pitch angle, so the pitch of the aircraft is controlled by means of the elevator. And this is the dynamical equation that we studied when we looked at the aircraft equation. So if you look at the longitudinal transfer function for the pitch, this transfer function is the transfer function we want to implement. So in the 6.4, what it is asking, it is asking us to find out the pitch altitude hold feedback loop. So what we need to do is, we need to construct the transfer function given on page. So for question 6.4, construct figure 6.15 and design the controller. So what I'm going to do is, now I'm going to go on to Matlab and I will show you how that can be done. But before I do that, I want to ask if there are any questions. Are there any questions? So if there are no questions, let me go to Matlab. So now you should be seeing my Matlab screen. And I want you to look at the same file, coefficient.m. And please note, in the coefficient.m file, you have a theta 3, a theta 1, and a theta 2. So I'm interested in finding values of a theta 1, a theta 2, and a theta 3. So these are the three values that I want. And I want you to open this file, altitude from the pitch loop. So once you open this file, altitude from pitch loop, you would observe that this is something similar, altitude from pitch. This is something similar. You can actually double click here. And then you will notice that this is the pitch loop that we want to implement. And so before I go any further, let me make sure everybody is with me so far. Open altitude from pitch, or you can just open pitch loop SLX. So once you open pitch loop SLX, you should be able to find this. So I'm looking for pitch loop. So what I'm going to do is, in this pitch loop, just this transfer function is the transfer function that is a theta 3. So I'm going to substitute the value of a theta 3, which is minus 2.71. Then a theta 1 and A theta 2. Click OK. So now you have the transfer function. This transfer function is same as the transfer function we just looked at a few minutes ago. This is the elevator control input minus, so I would say 45 divided by 180 multiplied by pi minus 45 by 180 multiplied by pi. So now then I need to specify the gains. So just to start, I'm going to say my gain is 0.9. KD gain, and I'm guessing here 0.3. And then again, there is another KD gain, which is K 1 over K DC value. And I'm going to assume that to be 4. And theta max value is say 20 divided by 180 multiplied by pi. Okay. And I'm going to save this pitch loop solution. And I will run this. And I will notice, let's see what happens. Clearly, the system is not working the way I want. Both the files are same. So you can use any of those files. So pitch loop solution. So what we will do is we can, so to add the altitude, we will convert this into a subsystem file and add it to the altitude loop. But it's okay. You can, both of these files are the same. So you can just add DC gain. DC gain is the quantity in the numerator. And I'm going to change the value of KP. See what happens. And now clearly the system is not behaving the way I want. So what I can do at this point is I can actually tune the gains. Let me see if the negative value works. So got some response, but not so great. So this is the perfect opportunity to actually tune the values. So KD, KP, you can tune these values and actually construct the response the way you want. Any questions here? So what you need to do for 6.4 is you have to use the appropriate transfer function and then use the appropriate values of the DC gain and then implement this pitch loop. Now, how do we go from pitch to altitude? So for that, you need to go from here, altitude from pitch. And when you go to altitude from pitch, so I'll show you what can be done. So currently our solution is not working. Our pitch loop solution is not working. So there is no point in going to altitude because altitude solution would be incorrect. But assuming you got this thing working, what you will do is You'll grab this, actually take this out from here. Oh, so delete, go to library browser, input, add input here. For some reason, my Matlab seems to be slow. Add this here as input. And then add an output here. And then feed this into your altitude hold loop. I have issue here. So what I need to do is connect this from here to here. And then connect this from here to here. I think I have a lot of Simulink windows open. That's why it's, yeah. So this needs to be connected here. And then you will have an out sync here. And then what you can do is save this. Sub. Highlight this. Right click. It creates the subsystem. Copy this subsystem. And go to your altitude from pitch loop and paste it over here. Oh, I know, because the Simulink is running in the background. So that's why Simulink has been slow. Stop. Okay. Now it will work. So delete. Add this from here. Now this is save as. solution. Now PAVA is the airspeed, which is 10. Oh, it needs 10, 30 pi theta DC gain, and I'm gonna call this DC gain 4. 4. Then altitude Ki 0.05 and altitude Kp is say 10. And now, but please note that our inner loop is not stable, so I don't expect this to work. But when you run this, yeah, you are gonna have an error that shows me, that tells me that we did not connect this loop somewhere. So let's see if altitude from input port is solution out 1 is not connected. So let me see if input loop side step pitch. There are some issues here. 1, 1. And let's see. This is the coarse hold loop. We don't need this anymore. This is not needed. Yeah. So first we need to fix the inner loop. Just make sure this inner loop is working correctly, and then get this loop inside the altitude control loop, altitude from pitch, and then make sure the system is working. Amplitude 5, 1, summing junction, list of signs, key P, key D. So I would encourage you to first make sure that this loop is working and then implement the same thing in this loop. So this is the pitch loop that we constructed. It's the system that you see here. This is the pitch loop. So we need to make sure that our pitch loop is working correctly. And to make sure that the pitch loop is working correctly, you need source, you need step, then you need sync, and you need scope. You have to finally implement figure 6.15. As long as you implement 6.15, this is to answer Michael's question. So clearly, the system is not working. So what I need to do is I will have to increase the value of gain and tune this so that the system step response is the way I want it to be. But clearly this system is not working. So I will have to tune the gains to make sure that the system is working. I'll try to increase the gain values. 30. But system doesn't. Let me see how much is the step time. Final value, say 20 divided by 180 multiplied by pi. So you will tune the gains, make this thing stable. And once this is stabilized, go back to this altitude from pitch loop, implement the loop here, and then show that your altitude is stable. I would encourage you to take a look at this and try to stabilize this. And then if you have any questions, I would be happy to answer those again on Tuesday's class. So this is all the project 6. So 6.15 is the one that you would stabilize first. And when you add that to the altitude loop, it will be 6.16. That is to answer Michael's question. You don't have to implement the disturbance. Tell me 6.16. You have to implement 6.16, figure 6.16 as 6.4, the pitch loop, pitch altitude hold loop. So just to clarify, question 6.4 is implement figure 6.16 on page 108 for Sagi. Any questions here? Okay, now I would like to quickly talk about project 7. If you look at project 7, the 6.5 is similar to what we have, altitude from the pitch. 6.6 is the gamma. So to answer Jacob's question, those gammas in the coefficient file, they are for Erosonde, they are not for Zagi. So as you can see, these are, just to answer Jacob's question, these are not for Zagi. You will have to substitute JY for Zagi, gamma for Zagi, gamma 3 for Zagi, gamma 4 for Zagi, trim values that you obtained from your trimmed solution from project 5. So alpha trim and theta trim you will get from your project 5. And then you have to change these values for Zagi and then obtain these coefficients. Does that answer your question, Jacob? Okay. So next part is airspeed from pitch. And I want you to go to airspeed from pitch loop. This sample file is given to you. This airspeed from pitch is figure 6.18. So let me give you some hints here for project 7. Project 7. 6.5, implement 6.17. So 6.5 is implement 6.17. 6.6 implement 6.18. Airspeed using the pitch angle. Six point seven implement 6.19. And I will discuss 6.8. But before I do 6.8, please complete the webinar, Matlab webinar, which is project 9, Matlab webinar on state flow. Okay. Any questions? So yeah, if you finish the certificate for state flow, that is good enough. Because for last step, 6.8, you will have to implement the state flow. Either you can use the state flow diagram or you can use the switch statement. But I will discuss how to implement 6.8 in next class. So if you are wondering, so Matlab state flow course. So this is the state flow on ramp that you should finish. And this is free of cost. So you will have to, once you understand this, then you can actually use the state flow machine. So Zubir, if you have done this state flow on ramp, you are good. Okay, I'm gonna stop here and answer any questions you may have.